lovely of... So, if we go through and look at our alkynes respond very similarly as the alkenes. Okay, they're still nonpolar pi bonds. So if we go under acidic conditions with water as our nucleophile, what happens? Okay, well, first and foremost, it reacts the same. We pick up a hydrogen, and we would end up with our alkene with the hydrogen on there, and then we would still have our positive charge. Okay? And realize that we still have the starting hydrogen on there. So now what happens? Number one, this is an exceptionally unstable carbocation, so that first step is incredibly difficult to run. Okay? It does not happen easily. Okay? Because we're making a very, very unstable product. Okay? Once we've got it formed, though, what can now happen? Water can act as a source of electrons, donate to our carbocation. We can have our water attack with our positive charge. We can lose a hydrogen, and we would end up with the first of our products. Okay? We still have a pi bond, so this theoretically could continue to react. Okay? And if we continue to react this, okay, how many steps? 1, 2, 3 steps. We could potentially foresee something like this being a product. Okay? Where all we've done is added water twice across the pi bond, just like we did when we used HBr. Right? Okay. Interesting observation came out of this, though. Instead of getting that as a product, we get that. You want to say that makes absolutely no sense. How could that possibly be true? And it turns out that that last sequence of steps is actually a relationship or a complex relationship between that red structure at the bottom, and it can go through the black structure, and it ends up right back at the blue structure. Okay? And a lot of this comes from recognizing the name. What is the name of the blue structure's functional group?
Ketone.
It's a ketone. And what is the name of the functional group in the purple structure? Okay. Shh. What is the purple's functional group? Shh. What is the purple's functional group? The rest of you are like, well, I don't want you to shush me. What the hell? That's weird. Oh, it's extra weird. We might go through and call it an alcohol because it has the OH. Okay, so we might say, well, that's an alcohol. Kind of like when we look at the structure now in that box, that we would call that one an alcohol, right? No, we don't call that one an alcohol. Well, how is what's in the black box the same as what's in the purple box?
Resonance.
It has OH.
There's a resonance between those structures. We have a carbonyl and an alcohol. Put close enough to each other, they become a carboxylic acid. We have an alcohol and a alkene. Put close enough to each other, they affect each other. Just like here, getting the carboxylic acid, here we also get another structure. That carbon-carbon double bond is an alkene. If we break down the name on that, as we've heard now a couple times, that is known as an enol. The enol should be familiar to you already, and this really shouldn't be a question, but it's okay that it is because everybody forgets it because I don't spend a lot of time talking about it. This we've already seen in Chapter 7. Okay? And Chapter 7 referenced the keto-enol tautomerization, and it's an insanely important tautomerization, okay, particularly for anybody that wants to do anything in, say, a medical field. Why? virtually all of our biochemical processes move through the keto-enol tautomerization. Okay? Virtually every single one. Okay? So if you want to understand why biochemistry works, you need to understand the relationship between the keto and the enol, because that's how we build structures in living organisms. Which is an awesome thing to discuss, and it would be a phenomenal thing if we were going to discuss that now, but it is actually second semester material. So all you are responsible for is knowing that this reaction results in the ketone form. We're still going through the same basic processes. We're still adding an H and OH, but the intermediate product, if you will, is an unstable structure that switches into the ketone. The ketone we don't undergo another addition with. Why not? What kind of additions happened first? Say that again? So there was a proton transfer. Okay, that very first step, we added a hydrogen to our structure, and at the same time lost a pi bond. That mechanistically is known as what? An electrophilic addition. Electrophilic additions are phenomenal reactions. They tend to work, though, for what type of functional group? Alkenes. Be more broad. Because alkynes are also there. That's not being more broad, that's adding broadness or adding specificity. Make it broad.
Non-polar pi bonds.
These work with non-polar pi bonds. Okay? An electrophilic addition are non-polar pi bonds because you're now only looking at the reactivity of the pi bond, which means the pi bond acts as a nucleophile. We have to react it with an electrophile. That's why we get electrophilic addition. What is different about the ketone? It's a polar pi bond, which means we are not going to follow under electrophilic addition rules. That polar pi bond changes the reactivity of that structure and ultimately leads us into nucleophile addition, which is in second semester. So again, we don't get to talk about that this semester. Okay? So the ketone functional group or carbonyl functional group won't do any electrophilic additions. Okay? So we get a little weird thing there. A lot of people tend to just memorize this as a weird exception. It's ultimately not an exception, but if you want to go through and memorize, this is probably a half decent one to go through and memorize. It will pop up again by the end of the semester. Okay? Mechanism, we can get the big long mechanism. We actually already talked about it. You will notice that actually, you don't notice here. I thought you were going to notice. We're using H2SO4. It doesn't have to be H2SO4. It can be other very strong acids. Really what you're looking for is H bound to something. Okay? And that something needs to be incredibly stable. That says incredibly. That one I think is legible as stable. Okay? So sometimes you'll hear a reference to triflates. Triflates are incredibly stable structures as well. Okay? You're throwing in fluorine onto your structure instead of oxygens. Fluorine's being more electronegative. We're going to draw the electron density further into the structure, making it an even stronger acid. So to get these type of reactions to work, we need really, really strong acids. Okay? That's why the sulfuric acid is tossed in there. Okay? So, new question. Why are these now more complicated than the ones that we've been talking about last week? There's more pi bonds. Okay, well, more pi bonds shouldn't be a big deal. Nothing should really change. Okay? So let's take a look at the first structure. Where should I add the H+? Should I add it here? Okay, so in that circling fiasco, okay, we had about 2 people saying no's. and also switch to yeses. Does anybody want to venture forth and be like, why the hell did you say no at any one of those points?
The carbon with the tertiary.
Okay. So we've got a suggestion for, whoops, that's not the right thing to do. Okay, why did we say no to the green position? Does anybody else want to add?
Or are you saying why we're saying no?
Yep. Why are we saying no to certain positions? And I'm not asking the answer to that. I'm asking, is there another position that you want to be like, why did you say no to that? Which big circle?
Red one.
The red one was one of the ones that was said yes. In fact,
okay.
the red one was actually said yes. All the other ones were no's.
Okay, never mind.
So what I'm trying to get at is the remaining two purples. Okay. Does anybody ask, well, shouldn't the hydrogen go there? You want to ask that?
I said they shouldn't go there.
Okay, so that's not what I asked. Does anybody want to address why we should not put a hydrogen at either of those two purple circles? Okay, said another way, you understand that the hydrogen should not go at those purple positions. If you say yes, fantastic. If you say no, we need to talk about that. So are we all yeses? Okay, fair enough. Which one do you want to look at first? Green, red, or blue? What was that?
Red.
Okay, I heard a red. So we'll start with the red. If we place the hydrogen there, that means we aren't touching that terminal one. We're only placing the hydrogen here. Okay? It got placed there because we took the pi electrons and we reacted them with the H+, putting the hydrogen at that position. What happened to the other carbon of the pi bond? It became positively charged. So when we're trying to decide, is that an okay place to place the hydrogen, we really aren't asking, is it an okay place to place the hydrogen? What we're asking is how stable is that carbocation? If the carbocation is stable, then yes, that was a good place to place the hydrogen. If it's not stable, then we should probably try and place the hydrogen somewhere else. Okay? So if we place the hydrogen at that red position, do we make a decent carbocation?
Yes.
Reasonable. Okay? What do you want to look at next? Blue hydrogen, or blue position. The pi bond comes out, reacts. We aren't messing with the other pi bond. We're placing our hydrogen here, which means
Secondary.
where's the positive charge?
The other end.
At the other end of the pi bond. There, what kind of carbocation is that? Is secondary more or less stable than tertiary? Less stable, which means, given the choice, which of our two pi bonds should react? The red one makes more sense. It's going to generate a more stable structure. Okay? So the blue one is a bad position. That's why no was said. It generates a less stable intermediate. Okay? So, process of elimination, we can deal with the green position. We're still having that same pi bond come out and react. We've now lost the pi bond, but we've placed our hydrogen here. What happened to the other carbon? It became positive. What kind of carbocation have we formed? Secondary, which is more stable? The tertiary, which means the red position's the one that reacts. When I react that structure with H+, how many products do I get? 1. I only get the one forming that more stable carbocation. Because
trace amounts?
we're not even dealing with trace amounts.
Okay.
Nope. Okay. I thought the next places you were going is that your nucleophile could attack from the top or the bottom, and theoretically that can happen on the carbocation. Ultimately, we tend to ignore that, and it becomes assumed into our system. So we really only end up with the red intermediate. We'll end up with the products that come from the red intermediate, which we might say would be 2, because it could attack, the nucleophile could attack from the top or the bottom. Would we get 2 products? No, because that position would not be chiral. We have 2 methyl groups. So we would get two potential products, but those two products would be identical to each other. So we only see one product. How are we doing? Okay. So the structure on our left, that wasn't too bad. We had a couple things that we had to reason through, a lot of different stuff. Okay, so let's take a look at the structure on the right. Where should we place the hydrogen? Suggestions?
On the end.
On the end. That end?
Yes.
Not that end.
It's the same thing.
This molecule is symmetric, so we could place it at either of those ends. Okay? So because both of them are symmetric, we can ignore that half. Okay? Interestingly enough, I think we can place it sorry, I gotta process out the steps.
Oh, yeah, okay. No, yeah, you're gonna put the end. Because then the resonance hit.
Oh, never mind. I know where I'm going with this. Sorry, I missed a part. Let's add our nucleophile, Br minus. So for the structure on the left, our final product with the bromine would be here, yes? If we go through and do that same analysis with this structure, what we're saying is we place the hydrogen here, and our positive charge goes there. We would not have placed the hydrogen here because that would have put the primary carbocation without resonance. That was a bad path. Make sense? Is that a yes?
Yes, that makes sense.
Okay. So what products do we get? And there we go. We're all happy and done, right?
No,
What do you mean no?
there's resonance. So you can get two forms.
Where do you think the bromide should go? Shouldn't it go to this position right here? Yes.
Yeah.
Should it go to the positive charge?
What the hell are you doing, Mike? Negative bromide should go to the positive position. And yet, what am I drawing? Is that carbon positive?
Yes. Well, not in that structure.
It certainly doesn't look positive. But that's how I got this one. Okay. So what happened? This structure has an added complication with it. That added complication is that you have a resonance contributor. What does that resonance contributor mean? That means the bromide could indeed attack the back or that last carbon, or it could attack in between. Okay? Which means when we go through to look at our products, how many products do we get? We would get two products. Okay? And two vastly different products. And this is ignoring stereocenters, right? Because that's a whole nother fun fest that we could look at with this one. Okay? So we end up with two products. Why? What is so different about that two double bond structures versus this double bond structure?
The double bonds on the right are conjugated.
The right double bonds are conjugated. That conjugation changes the reactivity of the overall system because we have to recognize that we have resonance within conjugation, which means the positive charge can appear in various locations, which means the nucleophile can attack at various locations, and we get varying products. Okay? So which one is the major product? Why are you saying the one on the right?
The pi bond is more substituted.
So it being a more substituted bond, you're suggesting that this product is more stable. And that would tend to favor a thermodynamic argument. Does everybody agree that should be the product? Because if we look at its pathway, it forms the more stable carbocation. No, it didn't form the more stable carbocation. That product came from the least stable carbocation. Because that carbocation is less stable, what does that do to its activation barrier? It increases it, which means the thermodynamic product is not going to form as fast. The other one forms faster, which would then mean it is a kinetic product. This isn't a question of major and minor yet. What this is a question of is what are the conditions that force one product over the other? Okay? That decision is ultimately going to come down to your reagent conditions. What are the conditions that are pushing one over the other? Okay? That is a much more difficult question, and it usually centers at this stage on temperature. Okay? If we're at high enough temperatures, what happens? We would get the thermodynamic product. Which one formed first?
The kinetic product.
The kinetic product. But at high enough temperatures, what happens with the kinetic product? It's reversible, which gives me the opportunity to form the thermodynamic. The thermodynamic, being more stable, is now irreversible, and I form only the thermodynamic if given that time. What if I go cold and fast? Well, if I go at very low temperatures, what happens to the reversibility of the kinetic product? It becomes non-reversible, which means I only get the kinetic product. I can't reverse to get into the thermodynamic system. Okay? So this is one of our cases on where kinetics and thermodynamics plays a very important role in how we evaluate which products we get. And so we have to be a little bit more careful when we think about reacting these species. Okay? So we could go through and look at an energy diagram. We've already kind of talked about these. Do you want me to look at it? Yeah? Okay. There was at least a sort of yeah in the back, so we'll accept that. The reactant's the same. If we go through, we're going to form our intermediates. See if I can do this right. Intermediate blue and red. Okay, and whoop. Product blue. Which if you follow the reference above, very few people will catch that, and that's quite all right. If we go through, we've got our intermediates through the middle, and we've got our products at the end. Okay, if we look at our intermediates, red versus blue, okay, the red intermediate is higher in energy because it's a primary carbocation. The blue intermediate is a secondary, so it's lower in energy. If we go through to look at our products, the red product is lower in energy than the blue because it is a more substituted pi bond. So there's our red product. Our blue product is slightly higher in energy. If we draw out our energy diagram, sorry for the other bump in there, we see a crossover point. That crossover point is what's allowing us to recognize that we do have this issue of thermodynamic versus kinetic. Okay? What dictates which product we get has a lot to do with how much more stable the products are or how much energy we've provided to the reaction. The blue pathway happens faster because its activation barrier is smaller. The red pathway is a more stable product, so we could reference it dynamic. Okay? And that's ultimately where this is coming from. Okay? We might again ask, why might this be important? It becomes important when we push a little bit further on into second semester, and most of the first unit is talking about kinetic and thermodynamic issues, okay, because it makes a really big deal, okay, with a lot of our reactions in second semester. Okay. Where it becomes directly relevant for us in this sort of unit is in reference to the isoprene unit. Okay. Iso because you have the stupid little fishtail thing here. Okay. This would be an isopentyl group because how many carbons are there? There's 5 total carbons, so we get an isopentyl. The isopentyl can also be referenced as an isoprene. The isoprene is important because most of our biomolecules come from isoprenes. That is the building block, if you will, for all of our biological, or a lot of our biological molecules. Right? If we go through and take a look, we isolated limonene. Oh, shoot, is it not? There it is. Limonene is made up of 2 isoprenes. Right? So if you go through and break down that structure, I think this is the way we got to go. 1, 2, 3, 4, 5. We have 2 isoprene units. Those isoprene units were bonded with each other through a complex enzymatic pathway we don't need to stress about. Those isoprenes made limonene. You can go through and do this with a lot of your biomolecules, right? In particular, steroids. Right? If you've seen cholesterol, which I will probably botch, there. Oop, not a 7-member ring. Cholesterol has some basic structure-ish like this. Okay. And there's a bunch of random crap hanging off of it. Something. Okay. That big complex structure is actually just a string of isoprenes very carefully linked to each other. Okay. So the isoprene unit is a basic biological molecule. If you're interested in medicine or in particular natural product medicine, okay, because you want to make drugs, isoprenes are a pretty important fundamental piece to be looking at because we can take advantage of biological systems to make those things for us. Okay. The isoprene unit typically has dual reactivity with a pi bond, and sometimes with this phosphate, sometimes there's another pi bond on it. And it's that conjugated pi system that allows it that multivariability and reactivity. Okay? So, which gets us excitingly into chapter 12. So chapter 11, again, we're just taking a pi bond and we react it with acids. Okay? That pi bond can come from an alkene or an alkyne. It cannot come from a carbonyl because
It's not a monopolar.
carbonyls are polar pi bonds. We're only looking at our non-polar pi bonds. That's why we're reacting them with the acids. We need that strong acid to force it to react, to cause that polarity. Yeah, David, or did I interrupt you now?
Isopropyl then would be a 3 with a 4th hanging off of it, so it's one more than the longest chain, basically.
Your question was more appropriately timed earlier, but I just kind of skipped over you. Sorry.
Yeah. So that's isopropyl.
This is an iso. Okay, that is the iso functionality. If that is it, and this is now my main chain connecting out here, well, how many carbons are in that piece? In that red piece? How many carbons? Where do you see 4? See 1, 2, 3. The 4 on the outside that you're counting as a 4 is part of the main chain. So that is not part of the substituent, so you can't count that. All right? So that gets referenced as an iso with only 3 carbons, and we get isopropyl. Right? Have you heard of isopropanol?
Isopropyl alcohol.
Okay, or isopropyl alcohol? We have an iso group, okay, and then it's an alcohol. I have to add an OH. The OH has to get placed as the main chain. That's why we call it isopropyl alcohol. The alcohol is the main functional group. If this is going to be an iso group, where does the alcohol have to be located?
One of the two.
The ends part of it.
Do you see an iso anymore?
Okay.
If we look at how it's connected out, that's not an iso. That would be a propyl. It's a straight carbon chain. So that is not isopropanol. That's only propanol. To be isopropanol, it has to connect to the main chain. Our alcohol has to be the main chain here. Now I have an isopropyl. Okay? The main chain is that OH. To be an iso, it has to connect where I have that fishtail.
Okay.
Okay?
So it's only when it doesn't have another functional group that it's one. So you had isopentane, those 5 carbons in it with a little on the last page.
So if we switch this up to an isopentane, 1, 2, 3, 4, 5. Okay, we've got the iso functionality. Okay, but now there's only 5 total carbons, so this just gets called isopentane. It has the iso and it's got 5 carbons. Okay. What if I did this? Isopentanol.
It's still isopentanol, right?
It is not isopentanol anymore. What does it become? This is now going to be a butanol, okay, which is extra misleading because I intentionally left that circle up there. There's your longest carbon chain. It's a 3-methyl-2-butanol. Okay. The common names are not fun to deal with. Okay. That's where iso tends to show up as a unit. I don't recommend dealing with it because it can be a bit of a mess. Okay. So with our addition reactions, chapter 11, strong acids. The acid being the most reactive thing needs to be neutralized. The acid is supplying what? Hydrogen ion, H+. The H+ needs to be neutralized by the electrons of the pi system. That very first step results in a formation of a carbocation. That carbocation needs to be as stable as possible. Chapter 11. Chapter 12. Okay, we still have a relatively unreactive alkene or non-polar pi bond. Instead of adding H+, we're going to add an electrophile. That electrophile needs to be strong enough to force the pi bond to react. Okay? Because we're now using something other than hydrogen, that something other than hydrogen can have other forms of reactivities, which means these reactions can become vastly more complicated. Okay? And typically how they're formatted, and even in my opinion, surprisingly Cardy, has differentiated them instead of trying to come up with a middle ground that shows some overlap between them. The next sequence of slides is challenging to deal with because what we're doing is taking very different looking things and saying what do we have in common between them to be able to categorize them according to their reactivities. Okay? You don't have to like that. Okay? As with most things I teach and say. And you can just go straight off of the spider diagrams. In fact, I meant to drop those in here and just say you need to memorize them. Okay? Because that's ultimately what you're going to be responsible for. There's a lot of intricate pieces to be memorized in each of those. So if you can understand some patterns behind how and why they work, you can cut back on the amount of memorization and be able to look at a new reagent and be able to predict how it would react. Okay? That predictive ability is key. That's one of the things I want you to be able to do. Okay? Memorizing a bunch of reagents, there isn't anything for me to talk about. Okay? So, almost all of these involve some form of cyclic nature, either cyclic intermediate structures or cyclic transition states. Okay? So we need to be familiar with what things that's going to force on our structure. Okay? This means we get a lot more selectivity in our products. Okay, so we can force that a little bit more, which also means they're more commonly used. Okay, because I know exactly how it's going to react, I don't have this intermediate carbocation flopping around. I can force the reactivity a little bit better. Okay? So when we go through and look at these cyclic type structures, chapter 12 is looking at 3-membered cyclic structures. Chapter 12 is also looking at 4-membered cyclic structures. And then chapter 24 brings in 5-membered cyclic structures. Right? So each of those reagents that are listed there, you need to know what they produce. So number one, all of those react with alkenes, okay? And in some cases, alkynes. Right? So we have to be familiar with that so that we know what to expect when we get into those. Right? An alkene is going to supply how many members of our cyclic intermediate? When we go through to look at an alkene, it has pi electrons located between 2 carbons. So our alkene is going to supply how many of the atoms of our cyclic intermediate? 2. So when we move to the tri-intermediates, notice what have I got highlighted? A single letter in each of those cases because that single letter is representing the single extra atom added to the pi structure. Okay, so in the first case, I'm adding bromine. In the second case, I'm adding
Phosphorus.
phosphorus. No. What? Phosphorus begins with P. You're absolutely right. MCPBA is not a sequence of letters representing elements. It's a sequence of letters representing the name of the compound. Right? So who named it that? Which do you want to see there? MCPBA or metachloroperoxybenzoic acid?
I'll take the long version so you
Okay.
know what it is.
So the next part is P. What is the P referencing? So what's the atom?
Oxygen.
It's oxygen. It's referencing a peroxy compound. What is a peroxy? It's an oxygen-oxygen bond. That oxygen-oxygen bond is exceptionally weak, and that's actually what drives that reaction. Okay, or exceptionally, let's just say weak. Okay, so we're looking at an oxygen reacting there. And the next one, carbon. Why might you think that carbon's a little weird?
Because it's triple bonded to a nitrogen?
Yeah, that formula looks all sorts of weird. Okay. Last one, Hg. Mercury. Mercury is a very reactive species. We'll see it pop up. You'll notice I've got X2 here. X is not referencing halogens. X is referencing pretty much anything else I want it to be. Depending on what those pieces are, it somewhat alters the reactivity. Okay, so your primary focus should not be on what the X component is. It needs to be the mercury part. Focus on the reactivity of the mercury. In the tetra compound, remember, our alkene only supplies 2 positions. Notice in the tetra position, what do I have? 2 atoms highlighted because I'm forming a 4-membered structure. I need to be adding 2 more things into it. When we move up to the penta system, it's a 5-membered structure. That 5-membered structure needs to bring in 3 extra atoms. Osmium and oxygen, we're really only looking at 2 of those 4 oxygens. Permanganate, again, 2 of those oxygens. And then ozone, you're looking at all 3 oxygens somehow reacting in there. Okay? In each of these cases, what we're trying to do is look for patterns that would allow us to say, why are we seeing certain things happen in certain circumstances? Yes?
So the whatever's bolted is whatever's like the most reactive or what will be
The
reacting?
bolded things are the things that are going to be part of your ring.
Okay.
Okay? When we jump up to the penta structure, this one gets a little bit weird. How many different positions can react from our alkene?
2.
2. Penta structure means 3 different things are being added in there, or 3 things are making it into the intermediate. Only 2 can be connected to the carbon structures.
Okay.
Okay? Because we only have 2 sites of reactivity.
Okay.
Okay? With the tri and the tetra, both of those are now going to change reactivity. In the tetra, H is going to go to one position and B is going to go to the other. In the tri, what's going to happen?
One of them is going to attach to both of them.
Okay? That one needs to connect to both of those positions. That one needs to connect to both of those positions. Okay? So again, what we're trying to attempt to do is something that has not been at least published to my knowledge, because I haven't done that much research on it. Okay? But it's not in any textbook that I've looked at. We're trying to group these very different things according to their rough transitions so that we can come up with predictions behind them. Okay? So let's take a swing at some of these. With all of these, your pi bond is acting as a nucleophile. That nucleophile needs to react with a Lewis acid. Okay? Or we could reference it potentially a little bit better as an electrophile. Okay? That electrophile will have something connected to it. Okay? So what we want to do is think about what are the characteristics of our Lewis acid, okay, and our leaving group, okay, or whatever that connected piece is. Okay? So in the first kind of case, what I would argue is that that Lewis acid can also act as a nucleophile. So a single structure can act as both an electrophile and a nucleophile?
Yes.
Okay. And that might seem a bit weird at first, unless maybe we drew a resonance structure of our alkene, and what do we see? What does the alkene act as? Both a nucleophile and an electrophile. Okay? So this isn't that foreign of a concept. Our Lewis acid can act as a nucleophile. Okay? The conditions to force that are going to be interesting. Okay? So to act as a Lewis acid, it must accept electrons. What might that suggest about Lg? Okay? So in our first approximation here, what we're saying is that our alkene must come out and share electrons with the Lewis acid. It has to. Okay? That by definition must happen because our alkene is a nucleophile. If it shares electrons with the Lewis acid, well, it's got its octet. Why would the alkene be able to attack? What must be true of that Lg? It's more electronegative. Okay? Or
The same electronegative.
we could go with same electronegativity, or I like stable. That's a bit vague for me, though. How would you evaluate stability? Charge. So if your leaving group, say, comes off neutral, that's a good case. Okay? Or if your leaving group came off big, that's a great case. If your leaving group came off electronegative, you mean the one that you guys suggested earlier? Yes, exactly. Okay? If your leaving group came off and had resonance, that fits this category. Okay? So what we're talking about is that that bond must break. Okay? And it also has to break in such a way that that leaving group is stable. Because if it's not stable, what happens?
Undo.
It comes back and the whole process reverses. So as a condition number 1, if we look at that reagent that we're reacting with our alkene, we identify the Lewis acid part, and then we go, ooh, look at that piece. That would be a phenomenal leaving group. Okay? That's a really big tip-off that we're going to fall under this category. Okay? This category says 3-membered ring. Okay? So yes, I need that leaving group to come off. But the other piece is that the Lewis acid must act as a nucleophile. Well, how could a Lewis acid act as a nucleophile? What does a nucleophile have to have? There would have to be electrons. But if there's electrons, how could it be a Lewis acid? Okay? What we're saying is that this condition must be true. The Lewis acid has to have those electrons. And what must those electrons then do? Remember, what are we aiming for? A three-membered ring, where two of those atoms of the ring are the carbons of our alkene. What must those lone pair electrons on that Lewis acid do? They must connect to one of the carbons. So those electrons have to come back. Have to. That is some goofy, weird stuff. There's no way that could possibly ever come true. And this is where everybody in the lab can be like, but Mike, we already talked about this in the lab. This is why we take the lab. Yes, it is why you should take the lab at the same time. When we look at the alkene with Br2, what happens? What can you tell me about bromine? Elemental bromine.
It's a halogen.
Okay, it's a halogen.
Diatomic.
Diatomic.
It's very electronegative.
What do you mean it's okay on its own? You mean if you broke that bond and we had bromide by itself, it would be stable? Yeah. Okay, and that would be negative, and that would be a nucleophile. But that would contradict this reaction, right? Tons of electrons. There's no way it could react with the alkene. But because we know bromine is electronegative, what could that purple bromine do to the electrons in that bond? It could start to suck them away. What's going to help that bromine suck the electrons away? How about the presence of that alkene right next door, shuttling electrons into that now forming positive bromine, that Lewis acid? We can then eject the leaving group. At the same time, though, remember, there has to be electrons. Does that bromine that was just attacked have electrons? Yeah, it has 3 non-bonding pairs of electrons. It's got a ton of electrons. What can happen? Does that match the pattern we just discussed? Does our Lewis acid, the bromine, have electrons? Yep. Can it act as a nucleophile? Yep. Okay. Is our leaving group stable? Yep. That fits all of the patterns, and guess what we end up with? If we follow those arrows, we have a bond up to our bromine. We have Br minus now floating around. And we have a bond back to our structure. Would that bromine be particularly stable?
No.
Why not? It's going to be charged. Okay? If we add a little layer of context behind this, we just formed a 3-membered ring. Are those chiral atoms? Rhymes with yes. That's all I got. Yes, those are chiral atoms. Why has that become a problem? We would need to specify wedges and dashes. If I make the red one wedged, what must the blue one be? Dashed? It has to be wedged as well. Why does it have to be wedged? It literally can't make that connection. Okay? If we look at my forearm, I've got a bond up here to a bromine. Can I possibly connect up and down to the same atom? It literally doesn't work. They have to both be wedged. Okay? Doesn't work. Why has this become important? Well, have I shown some stereochemistry? Yep, which then means my final product, what am I going to have to worry about? I'm going to also have to worry about this R and S stereochemistry mumbo jumbo. Is this structure potentially stable?
No. As is on the board? No.
As on the board, that's a travesty to humanity because bromine doesn't want to be charged. That bromine is going to be already breaking away from the structure. Okay? Really, all it is doing is shielding the positive charge on the carbon. That's about it. And by shielding it, what is it preventing? it's preventing that bromide from coming in on the same side. It can't come in because what's there? Okay. We've got, here's a little emblem on it. It's a shield. It can't attack from the same side, so what must that bromide do? It must attack from the other side, which means if I go through to look at my final answer, what happens? I'll get a bromide wedge. That position didn't change. What happened to the other one? It must be dashed. I get the bromides being added on opposite sides of that pi bond. One of the references people like to use is trans. Trans is an adjective. What just happened there was an action. I don't need an adjective. I don't need a description of a noun. I need a description of a verb. I would need an adverb. And because we've got the English language, we use a different word to represent that. This is now
A backside attack.
sin addition would be if they were on the same sign, sin cis.
It's on your plate, anti.
This is an anti-addition. The two new groups were added trans to the old pi bond. So if I look at that structure, I can reference it. What we just described was an action. I have to reference it as an anti-addition. Okay, why? Adverbs and adjectives. Blame the English language. Okay, that's where it's coming from. Okay? That said, if you were having a conversation with me and you said, well, I got the trans product, I would accept that. Okay, it's a little bit iffy. Trans is in reference to cyclic structures and pi bonds. Do you see a cyclic structure in your answer? Do you see a pi bond? No. So calling it the trans product isn't the greatest thing to do because it doesn't appropriately match to that system. Make sense? Yes?
So the final product, would we have like enough?
So, how many products would we obtain at the end of this reaction? 2, because
The other bond can
when the pi bond reacted with this bromine, we said the bromine was formed wedged. Doesn't the pi bond have electron density on both above and below?
Yes.
Yes, which means that step had
Dash.
2 products, which then means the next step is going to have 2 products. I would have to evaluate the relationship between those. Admittedly, I suck at doing that without having the drawings. I'm going to guess they are going to come out as enantiomers in this case. Okay? But we do have to be a little bit careful just saying, oh, they're enantiomers, diastereomers, or any of those things. Okay, but yes, we do have the potential for 2 products because you have a pi bond starting the reaction.
Never mind. Answer my own question.
Cool. So we went through and looked at a specific example. Yeah, I'm not even going to ask at this point because I just deleted it all. Our Lewis acid reacts, our leaving group leaves, there's our cyclic intermediate. We can then have a nucleophile come in and attack. In the example we looked at, what was the relationship between the nucleophile and the leaving group? I can't go back, so you better help me out. What was the relationship in the previous example between the nucleophile and the leaving group?
They're the same.
They were the same. They don't have to be the same. So when you look at your reagents, be careful to look to see if there's another species that could be acting as a nucleophile. Sometimes it's obvious, sometimes it's not. So just kind of watch out for that. Okay? You'll notice that I do have a question mark in that last step. Why have a question mark there?
Does this actually happen?
Does it actually need to happen? Why would it not need to happen? If this structure, okay, which admittedly I have a positive charge on, but it didn't have to, if that structure was stable, if the 3-membered ring was stable, there are cases where it is stable. In which case, what happens? It stops. There are also cases, like with the bromine, where it forms an unstable structure and it must continue. That's why we have to look at that question mark. Okay? Kind of makes sense? Starting to get the idea behind how we're piecing these things out? Okay? And again, I'm not saying it's easy. Okay? In fact, I think it's incredibly difficult. It took me like 6 years to even think about approaching this. Okay? What happens if our leaving group is tiny? Okay? Let's think about it. Look, pi bond still has to come out and react, right? So, ta-da, pi bond comes out and attacks. But now instead of the leaving group being nice and stable and large, it's tiny. Okay? If it's tiny, what does that mean? Well, those electrons would break off onto the leaving group. But you're shaking your head. You're shaking your head no, because it's tiny. It's not stable on its own. Okay? So let's just kind of walk through that a little bit. Those pi electrons come out, react with the Lewis acid. Here's our leaving group. And the electrons go to the leaving group. So if we think about kind of, let's just say it happens. We'd have our bond, right, between the Lewis acid and our alkene. What happens to the other carbon of the alkene? It would now be positive. What was the leaving group? It's tiny, and what did it leave with? Electrons, which means it would be negative. If it's tiny, can that negative be stabilized? No. So if it's going to get forced out, it needs to get forced out someplace where it can immediately be stabilized. I wonder if there was something positive nearby.
Yes.
Oh. So what happens under these circumstances for these four-membered transitions is that our Lewis acid and our leaving group align with the pi structure. The pi bond comes out, reacts with the Lewis acid. The Lewis acid is now excess of electrons, so the electrons in that bond immediately come out and react with the other carbon. The result is what we would show as a transition state. And in this transition state, what have we formed? A square, also known as a four-member transition state. What is that going to do to the stereochemistry at the end result? Okay? Because if we went back and looked at the other one, with that transition state, they were all on the same side, which means here they're going to be all on the same side. If we propagate that out to an end result, if the Lewis acid was wedged, what must the leaving group also be?
Wedged.
Also be wedged. They won't be connected to each other at the end, but it has to come in that alignment. Okay? Do I need another step?
No.
We're looking at it right now. It looks pretty stable, so we would say no. It is possible that there could be another step, depending on what the atoms are that are connected. Okay? So what we would need to do is evaluate what those pieces are and decide, do I really want a metal stuck to my carbon? How many of you have seen metals stuck to our organic compounds? Okay, so it's probably not a good idea to put it there. Why might it be a good idea to put there? Why have we not talked about them?
Because metals are really, really weak at holding on to electrons.
Metals are weak at holding on to electrons, which means that bond is ultimately
Polar.
highly reactive and unstable. So we're going to want to do something to break it off. Okay? Depending on the reaction we're looking at, that might require special reagents. It might just be the end of it and it just falls apart on its own. Okay? That's why we have to look at the detail behind a lot of these reactions. Okay? So when we look through this, our overall reaction is an addition. Okay? This helps us predict the product. Okay? We know the Lewis acid has to be attached to one carbon. The leaving group has to be attached to the other. Okay? When we go through and look at the structure and the mechanism, this can give us information about the stereochemistry. It can also give us information about the regiochemistry. Notice with the alkene we started with, Which of those carbons was more likely to attack the Lewis acid? Why both? Symmetry in the structure. What happens if we make it asymmetric? If I do that, so now let's just clean all that up. Let's not worry about any of that. What would my product be? The Lewis acid should react with which of those two carbons? What charge was the Lewis acid? It's positive. It's receiving electrons from the alkene. So where should the Lewis acid be connected? Well, which of those carbons is more negative? Left or right? Right, and not just because it's right? You would do resonance, more stable carbocation. So we would put the Lewis acid here. Which means where should I put the leaving group? To the other carbon. What kind of bond should I use for that leaving group? Y dashed. What we're dealing with is that cyclic structure in our process. So if we recognize the Lewis acid and the leaving group, actually, sorry, I misspoke. And you're not wrong, by the way. I appreciate that. Lewis acid and our leaving group. Why would you know wedged versus dashed? If we just know the reaction is an addition, I know where the Lewis acid goes, I know where the leaving group goes. How do I know the wedge and the dash? I need to know the mechanism. So I would go back and look at it and say, well, that leaving group is damn big. Which means the leaving group is going to have to attack from the backside, which means when I draw out my products, the alignment between those has to be opposite. And if they're small leaving groups, they should be on the same side. So the overall reaction can be predicted just by looking at the pieces. Okay? Some of the regiochemistry, so where did the Lewis acid go? Where did the leaving group go? That's regiochemistry. Which atoms did they connect to? That's looking at resonance. So very simple steps into our mechanism and structural effects. The exact spatial orientation of those pieces falls very squarely in the mechanism. Don't know mechanisms? How would you know the answer? You can. You memorized it. Okay? There's lots of reactions. You can do it, but that ends up being your only recourse. That's why we talk about the mechanism, to give you that context so that you can start to kind of piece your way through it. Okay? But on an exam, you may not get that time. Use your regiochemistry. Use the basics of those steps, positives and negatives, to nail down where the pieces should go most likely. Eliminate some answer choices. If you get time, dig into the mechanism. Make sense? Okay. Okay, so the question mark on that last part, again, it depends on that intermediate structure. Right? If we've got some weird, funky things attached to our structure, maybe we'll continue on. If they look fine, then we just stop. We really only do that in one case. Okay, for the most part, we continue on. Okay. So how can,
What if you had something like where there was a bunch of resonance bouncing around? Like say you had like those were all three alkenes, and then, you have the 4 carbons with 3 pi bonds, and then you get like double resonance to that bromine.
So I'm going to sidestep this in 2 ways. 1, I don't know what you're talking about. 2, it sounds like what you're talking about is conjugation, and conjugation we won't worry about until second semester.
Okay.
How can a structure be both an electron acceptor and a donor? Right? We want atoms or structures with lone pairs, so they can be a donor, and we also want weak bonds. What makes them weak bonds? We're looking for a good leaving group. Okay? So, what do you think? First structure. Do we have lone pairs? Yes. Do we have a good leaving group? Yeah. Does BR2 fit the pattern? Yep. We're going to get 3-member transition states. Okay? How about the next one? Do we have lone pairs? Yes. Do I have a good leaving group?
No.
No. Why is that a horrible arrow to show as a leaving group?
Because there's still another bond.
So, and this is something we do have to be careful. We go, a leaving group does not necessarily have to leave the structure. Okay? A leaving group just means that electrons have left that atom. Okay? Why is that arrow a bad option?
The carbon would be charged.
Yeah, the carbon would be charged, which could be a problem because carbon can't stabilize a negative charge. Why not?
It's too small.
Small and
Not very electronegative.
not very electronegative. So we can use our charge examples to reference that. Okay? How should the electrons in that pi bond move? Towards the oxygen. Okay? So that structure, while it has lone pair electrons, it doesn't have weak bonds in the sense that they would break in that fashion. They would break in the opposite fashion of what we want, which means I'm not going to do this. That reagent isn't going to work for this. Doesn't fit the pattern. Make sense? How about the last one? We got electrons up the yin-yang. Okay? Electrons right here. There's a negative. Does it have a weak bond?
Not there. Not there.
No, that one wouldn't work. So that's a bad option. Okay, we have electrons. Does it have a weak bond? No, that would be horrible. Could we go there? Why opposite? Yes. Oxygen's more electronegative than mercury, so that one doesn't make sense. Okay, well, the other side's all more the same thing. How about the mercury? The mercury has lone pair electrons. Could the electrons do that? Why? Oxygen can stabilize the electrons because it's electronegative. Why else? This structure has lots of resonance to stabilize it. So do we have a source of electrons and a weak bond? Yeah, guess where this reagent shows up? 3-member transitions. Or 3-member intermediates officially. Okay? So we're trying to find those patterns to help us group the reactivity so that we can predict. Sometimes that information is buried from us or hidden. How? When we look at this first species, how is it given to you? Do you see electrons? Do you see a leaving group? Okay, we've removed structural information. By writing it that way, what are we testing on?
Our understanding all
A couple things I would argue. First and foremost, by writing it that way, we are literally testing, did you memorize it? And that's it. Right? What I've been asking you to do is to immediately see that and to accept that you will have to draw. And so the instant you see BR2, you are already writing as you read out the question. Now that you have it drawn, you can see that information. Okay? Because there isn't this pause of, well, what does that look like? No, you've already drawn it. Okay? For the last one, because we said that one fits the pattern. Okay? Similarly, not given to you nicely. Does anybody see the electrons on Mercury? No. Are they there? Yeah. How did you know? That one sucks. You're supposed to just know it. That one's supposed to be memorized. Okay?
Draw it out though, right?
You could attempt to draw it out. You're going to have a hard time drawing that Lewis structure because Lewis structure, as you've been trained to do it, is based off of what kind of compounds? Carbon compounds and ultimately covalent compounds. Why is that a problem?
Isn't that a...
That's an ionic compound. It doesn't fit the patterns of Lewis structure as neatly or nicely, on top of which mercury is a transition element. Its electron configuration in the Lewis structure is a giant source of fun. Okay? What is this AC? What is this OAC?
Acid.
Okay? The O is referencing the oxygens. The AC is referring to this piece, known as an acetyl. So OAC is saying take an acetyl and put an oxygen on it. What does that generate?
Acetone.
Well, that would be 2 carbons, 3 hydrogens, and 2 oxygens. With a negative charge, because we have a metal to a nonmetal, and we have acetate. You mean I had to memorize the complex ions from Gen Chem? Okay? That's where it's coming from. No, you didn't have to memorize it, but that's where those names are coming from. That's why the AC is dropped on there. Okay? On a test, you're like, what the hell is AC? Just raise your hand and ask. Okay? If at any point you see something on the final that you're like, I have no idea what this means, ask me. Okay? I may not be able to answer, but ask me. Okay? Okay, so if we look at the cyclotri structures, this is trying to set it up so that we can see those intermediates. Okay? We're aligning it now with that pi bond with the p orbitals in the plane of the paper. We can get 2 end results. Why? We can attack the left side of the structure or the right-hand side of the structure. That sets us up with 2 possible results. Notice in both those results, the electrophile and the nucleophile are added on opposite sides of the original pi bond. Okay? In this case, what is the relationship between those 2 structures?
Enantiomers?
Like,
Oh, wait a minute.
They're identical. Okay? Since we haven't specified what those 2 things are, that's not a chiral atom. Same deal up here, which means those 2 structures are the same. Okay? I still get 2 possible products because of that pi system. Okay? But what we're trying to do is emphasize the alignment of all of those groups. Notice that as we move through, these things don't switch sides. If we dropped in a 1 and a 2, this is still 1 and 2. This is still 1 and 2. We don't start changing those. What might happen is that when we look at this product, what is special about the bond connecting those? That is a sigma bond, and that sigma bond can freely rotate. So after we run the addition, what they might very well do in your answers is spin the single bond, making it look like the electrophile and the nucleophile were added on the same side. And you go, oh, well, that's clearly the wrong answer because they're on the same side. Watch out for a sigma bond rotation. Okay? Okay? And I can see people already being, oh my God, yes. Okay? What I'm pointing out is the complexities. Okay? I want you to be aware of those complexities. That doesn't mean every question is that. If you suspect something like that is happening, just skip it. Move on later. Come back to it later. Okay? But you need to be aware that that's happening. This is all a simultaneous system. That's why those things all get locked down. We still have to watch out for a sigma bond rotation at the end for an answer choice. Okay? If we go through and look at each of these reagents, okay, we're putting on, let's see if I can color code this. Electrophile leaving group. Electrophile leaving group. Electrophile leaving group. This one gets a bit weird. That one gets weird because if I break that down and look at that structure, carbon, go away. Let me finish this before class ends. That carbon will act as a nucleophile because it has a lone pair of electrons. Whoops, and I missed the negative. What's extra fun about that is that our pi bond can still attack it. Why can it still attack it? There's electrons there. There's no way in hell it could possibly react. What does it have in that nice bright green? A positive nitrogen. Does nitrogen want to be positive? No. So what happens? It can steal electrons from that carbon, making the carbon. All sorts of weird charge things come out of this one. Okay? An empty p orbital, so we can dump electrons in, and then that negative charge can share back in. Okay? Why would that nitrogen kick off like that? What would that resulting structure look like? What is that species? Elemental nitrogen, which is what phase?
Gas.
A gas. This reaction or reagent is diazomethane. Azo is nitrogen. Diazometh, 1 carbon methane. This reagent is so insanely reactive in this fashion that I was told I was not allowed to run it as a graduate student. Okay? The postdoc that has been doing chemistry for 20 years was told that he should not run it. Okay? For me. Okay? People that run this reaction regularly are missing fingers. Okay? It explodes violently. You notice all your glassware has the frosted joint so that you can form a nice tight seal. By putting the frosted joint together, it creates enough friction that it'll cause that compound to explode. Okay? It's insanely reactive. Okay? So all of the glassware involving that is all non-frosted glass. You have to use silicon, all sorts of fun stuff. Okay? What is the end result? If the pi bond comes out and reacts, the nitrogen or the carbon must also come back. What have we formed? A 3-membered
Cyclic structure, intermediate. Actually, I don't know if it's intermediate. That's neutral?
That's neutral,
Yeah, okay.
which means
That's the end.
that's the product. Nothing else happens. We form a cyclopropane. Why might you go, holy crap, how can we do that?
Because it's just ring strain.
Ring strain. We might say cyclopropanes shouldn't form. How do we make them form? We use a species that explodes when we twist glassware. Okay? That's how we make them. Okay? So we'll pick up there. I apologize for talking long for those of you